So first, let us discuss Stone-Weistrass theorem. We will do some application. We will discuss some applications of the theorems we have learned in the last two classes. So first, we will talk about Stone-Weistrass theorem. This is the first theorem Nirupama proved. Okay. So the theorem says the following: let X be compact. I mean, for the time being, we can take compact metric space. I don't know if she assumed. We can take compact metric space. Then if we have an algebra contained in C of X is a Banach space. Okay. So that can be easily proven. If we have an algebra means it's a vector space and it's also a ring where you can multiply, and these two operations are consistent. I mean, in algebra, a ring means you have an addition and multiplication, and there is a distributive law which connects these two operations. Now you have furthermore, it's an algebra which is also you have a topology on this. So all those algebraic operations should be continuous also. That will be guaranteed by the norm. C of S is a norm, and norm of C of X, so this is with respect to norm F infinity, which is equal to supremum of F of X. Supremum of T in X mod F of T. So this is so I mean, I stated for the complex thing. I mean, she has proved it for real, and then I think she has given the complex case as assignment, so which you will prove. So I will take it as complex one. Okay, taking values in complex way. Okay, so I mean, I was talking about algebra. So all these algebraic operation, multiplication, addition, they are all. I mean, if you have a norm, then by triangle inequality, addition is continuous. And similarly, you have this inequality, norm Fg is equal to I think norm is less than or equal to norm F times norm G. So from that, it will follow that the multiplication is also continuous. So the algebraic operations are continuous. So it's a nice algebra. And we don't assume that A is closed. So suppose, and if the following conditions are satisfied, so if so Stone-Weistrass theorem says the following: if A separates points of X and contains constant, I mean, contains constant, you can replace it by A is a unital algebra. Unital means the constant function 1 is there. Then because it's an algebra, all constant functions will be there. Contain constant, then A is dense. Okay, I think this is the theorem. Dense in C of X. Okay. So some of the consequences. So this is the theorem. Then some of the consequences, for example, you know that the polynomials are dense in C01, for example. C01R, if you want to take just polynomials in one variable. If you want to talk about polynomials taking complex values, then you have to take polynomials in Z and Z bar. Okay. So, I mean, you may think that this is Weistrass theorem. The first statement is Weistrass theorem, which is actually used in Stone-Weistrass theorem. She has used it, but that is not strictly needed. You can actually, it is enough to prove that the function, square root function, x going to square root of t going to square root of t, if you prove that that function can be approximated, I mean, that kind of function can be written as uniform limit of continuous function, then it is enough to, I mean, that is enough actually. That is what being used. You will be proving that some square root of something is approximated by continuous function. That is what being used. So you don't need the whole Weierstrass theorem. It is enough if you can approximate square root function by continuous function. Then you can prove the Stone-Weistrass theorem, and from that this will follow that all polynomials are dense in C0, 1. Did I say? Yeah, no. I mean, I said something wrong. That is stupid actually. The actually square root function can be approximated by polynomials. Yeah, I said continuous function. Square root function can be approximated. It's enough to prove that the function square root function is can be approximated by polynomials. Then you can, it is enough to, that is what being used in the proof of Stone-Weistrass theorem. So once you prove that, then you can prove Stone-Weistrass theorem. From that, it will follow that all polynomials are dense here. Okay. Similarly, polynomials in Z bar. You have to take Z bar and you have to take complex coefficients. Okay, complex with complex coefficient, of course. Are dense in C01, taking values in C. The third statement is, for example, trigonometric polynomials are dense in, this is used in Fourier analysis. So trigonometric polynomials, you take A equal to all those things, A0 plus AN, AK, maybe summation, AK cos kx, summation k equal to 1 to n, plus summation L equal to 1 to m, B L sin Lx, okay, where I mean k and L are integers, it's written there, where A0, these are all just real numbers, A0, BK, AK, BL, they are all real numbers, okay. So this is dense in, so I want to use a notation. This is dense in C. I mean, this is, maybe I will just call it over circle, but write it as the functions on real line. Where this is all those functions f in C01 such that f of 0 equal to f of. So I mean the endpoints, the values in the endpoints coincide. So these are all the functions. These are all periodic functions. I mean, these are all any periodic function on the real line can be considered as a function on just 0, 1 or any other interval AB. Then I mean, this statement is true for any other AB also. I mean, if it is true, something is true for C of an interval 0, 1, then it is true. I mean, you can change the statement and it's true for any interval also. You can change it correspondingly. Okay. So this I want to give it as an assignment. Okay. There is not much to do in assignment. First, you have to check that it's an algebra. Checking that this is an algebra will take some manipulation, trigonometric manipulation. You have to use formulas like cos A plus B sin A plus B formula, which you must be knowing. So this is assignment. I mean, one is today's assignment 1. I'm basically going to give assignments today and stop. So this is assignment 1. So then proving that separates point, all those things will follow. It's not going to be difficult. Okay. So trigonometric polynomials are dense here. And so one more thing I want to say about those polynomials. This is just an exercise. You don't write it as assignment. If you have any function f in say C01, okay, and suppose, I mean, this I'm not giving it assignment because the similar thing you will do in a different assignment. Next I will give. So suppose f and g and f are in C01. Suppose integral 0 to 1 f t power n f of t power n dt is equal to integral 0 to t of t power n dt. Suppose this is true for all n. Okay, then f equal to g. The proof is easy. So you just have to prove that integral enough to prove integral 0 to 1 f of t power n dt equals 0 implies f is 0. That's what you have to prove. To prove this, you can I mean f bar is a function which you can approximate it by t power n. Okay, so then I mean which you can approximate by polynomials. Since this is this integral is 0 when you hit it against t power n, it will be 0 when you hit it against any polynomials. So because of that, it will be that will be 0. So, but then the convergence is uniform. Polynomials converge to f bar uniformly. So you can take the limit inside by dominated convergence theorem, and because of that, it will follow that mod f square 0 to 1 mod f square is 0. So f is positive, so f should be 0. So, okay, so that I have orally given the proof of this exercise. Okay, this is an exercise. The next assignment I want to give is the following. Okay, so prove that e power I n x, here we need n to be in z. Okay, you need it in, you have to take all integers, z, because in complex, this is a complex case where you need the conjugate to be there. Okay, is an orthonormal basis. I'm sure you have studied it in the last semester, which you usually write it as O and B, orthonormal basis for the Hilbert space L2, 0, 1. There is some, I have to change it. This is, I think this should be I 2 pi I nx. Okay. So then only if you take the, so proving that orthonormal basis is easy. If you take two different things, if you take the integral of any, I mean, then you will get an n minus m. If you take 2 pi I n x, 2 pi, and integrate it with 2 pi I m x bar, that is the inner product between them, which is the inner product between them. Then you will get in the inside the integral, you will get an n minus m. And for any, so if n is different, then the n minus 1 will stay as an integer. Then for any integer, integral of e power 2 pi I n x, that is 0. Okay. You integrate it and the end point it will be 0, same, and it will be 0. You can check it's 0. So because of, and then if you take the, if you take the same function, if n is equal to n is equal to m, then it is just 1. Yeah, and it says mod 1, so the integral will be 1. So this form, this is a, so you can prove that the integral of en em, but if you call it en or something, then the inner product of en em is delta nm. Okay, that you can easily prove. Then you have to prove that it's an orthonormal basis. To prove that it's an orthonormal basis, so you have to assume. Do you know this fact? Use this fact. I don't know whether this is proved in the last semester. This is contained in L201. Is dense. Do you know this? I mean, in the sense that does anybody not know this? I'm sure some of you should know. I mean, those who attended my course in the last year should know this because this was done. So anyone who does not know this, tell me. You can look at, or you can look at the earlier last year course, or you can look at any book, standard book. Okay, I think Shiva Atreya Sundar's book has this. Or Kesavan book will also have this. Okay, so how will you prove this? See, you have to approximate any L2 function by functions in C01. So by continuous function. So, but in any L2 function, is a limit of uniform limit of simple functions. So it's enough to approximate yes indicate. I mean what do you call what I call as indicator function or characteristic function is 1e. Okay. So this indicate this characteristic function you have to approximate. To approximate a characteristic function, you have to use what is called a regularity. Okay, regularity means any measurable set can be approximated in measure by an open set from the top. Yeah, open set from the top and closed set from the bottom. Okay, so that is what is regularity. And if you use, I mean, this is something like this. There exists. If you have compact set, then there exists. This is compact. 0, 1 is compact. There exists a compact K and open U such that mu of such that E is contained in K is contained in E is contained in U such that mu the measure. So this is true for any measure. Here I'm taking Lebesgue measure. Okay, this is C of X. Any compact set for any compact set X, C of X, X compact, C of X is dense in L2 of X for any finite measure. Okay, this is true. I mean, here with respect to any finite measure, but here I am only taking the L2, I mean, the Lebesgue measure, which is a finite measure here. So then mu of this E, mu of U minus E, set difference is less than epsilon. For every epsilon, you can find, given any measurable set E, for every epsilon, you can find a K and a U satisfying this condition. This is what is called regularity. I think again, this is rather, I hope this is proved last semester. If it is not proved, you can look somewhere. And you have, from this, it will follow that you can approximate an indicator function by continuous function in epsilon uniformly. And from that, it will follow that C01 is dense here. So I want, I mean, you can assume and prove this. You can use this fact. Okay. So once so you have to use this fact. Once you know this fact, then you know that this e power inx, linear combination of e power 2 pi inx, this linear combination of these functions are dense in C01, which is, I mean, in uniform now. So, but then C01 is dense in L201. Now you can approximate any function, then you can approximate any L2 function in terms of this linear combination of this uniformly. Then you can show, or you can, I mean, you just have to show that the integral of, if you have any function f in L2, then this is equal to 0, implies f is equal to 0. And this is just the integral, f en bar equal to 0, or en is enough because bar is also there. En equal to 0 implies f is equal to 0. Okay. Now you can prove, I mean, then this will prove that with respect to any continuous function can be approximated by linear combination of this en uniformly. So because of that, you can take the limit inside, and it is true that integral fg equals 0 for all g continuous. Okay, C01. Okay, and because of that, so that those continuous functions are dense there. Because of that integral, so because of that, f should be 0. Okay, because if something is orthogonal to a dense subspace, then it is 0. Okay, you know that. That you must be knowing. So you have done some basic Hilbert space theory, from that to follow. So I want you to prove this. I have given all the required ideas. Okay, you just have to write it. So this is assignment 2. So this is for Stone-Weistrass theorem. Now I will prove something in Stone-Weistrass theorem, which is very easy. It was so this is another version of Stone-Weistrass theorem. This also you can say Stone-Weistrass theorem. Theorem is the following: let A contained in C of X, not 0, 1, C of X, X is compact. I better assume metric space. I mean, it is enough if it is compact T2. But I assume metric space for the time being. I don't think I will be using it anyway. So A is contained in C of X. Then you want to prove, you want to assume A satisfies the following condition. A, I mean, in Stone-Weistrass theorem, it separates points. Okay, that is given xy in X, there exists f in A such that f of x is not equal to f of x. That's what it means by it separates points. Okay, then either A is equal to C of x. I'm not assuming A contains constant. Then either A equal to C of x or there exists a x naught in X such that A is equal to all those f in C of x such that f of x naught equal to 0. Okay. I mean, this is something smaller. Oh, sorry. F is closed. I assume F is closed. I mean, it is dense in such a thing, so I assume F is closed. Is it closed? Closed subalgebra. I am not assuming it's unital. It need not contain the identity or constants. Okay. So I think the theorem is fine. A is a closed subalgebra. It separates points. That's the only assumption. Then either A should be all of C of x or A is of this form. There exists x naught such that A is like this. Proof. So if it contains constant, if one is in A, if contains constant, then A is equal to C of x. That we know, right? That follows from Stone-Weistrass theorem. So we assume that one is not in A. That is, it does not contain constant function. Okay. Now, so let A prime equal to A direction. This. I mean, this is just the usual vector space direction, which is just f plus lambda times 1. This 1 is just identity function. Okay, I mean, it's just the constant function 1, which is the identity for this algebra C of x. Okay, which is the multiplicative identity for this C of x. F plus lambda 1, lambda is in C. So I think it should, it's a, I mean, it should contain the, I should assume that F is in A, then F bar is also okay. It's a conjugate subalgebra. Okay, whatever. Okay. Then by Stone-Weistrass theorem, A prime, this is closed. This is clearly closed. I mean, if you take a closed subspace of a Banach space, and if you add one more dimension, it will still be closed. You can just check it just by writing down the sequences and other things. Okay. I mean, if something is Cauchy in that, then each of them will, I mean, if you have take a sequence like this, f plus lambda n 1, okay, then it will imply that since lambda n is not there, if this is Cauchy, then fn is Cauchy, lambda n is Cauchy. Because of that, this will also be closed. Okay. I mean, it's actually you can assume that it converges to something, and you have to show that the limit is there, and it will be there. Okay. So this is closed. So by Stone-Weistrass theorem, this is equal to C of x. Okay. Now I have to produce a x naught such that yeah, this condition is satisfied. So I have to produce an x naught. Suppose f of x not equal to 0 for all x in x. I want to say this is not possible. Okay. Then f is invertible. Then 1 by f of x is in C of x, right? So this is, sorry, 1 by f of x for yeah, no. I want to say the different thing. What do I want to say? I want to say the identity is there. So it should not, I mean, there is a point x naught such that f of x naught is 0 for all f. So suppose there does not exist such a point. So suppose, so this just means for all x naught in x, there exists a f in A such that f of x naught is not equal to 0. That's what it means. I want to say that there exists a x naught such that f of x naught equal to 0 for all f. So if that is not true, then for all x naught in x, there exists a f such that f of x naught equal to 0. From this, I want to say it contains constants. Do I have to use the compactness or something? I want to say this is not possible. Then it will contain constant. That's what I want to say. Okay. That means I want to say it contains 1. So f of x naught is not equal to 0 means it's not 0 around an interval around f x naught. So you can, so there it will be in that interval, you can take 1 by f of x naught, and then you can find a function which is 1. Then there is a continuous function which is, so then by dividing it by 1 of x naught, you will get you will not get a constant everywhere. And nuts. Anyone has an idea?
If we take for any x naught and if we take a neighborhood, if we take a neighborhood for a particular f where f x naught is not equal to 0, and then that neighborhood, those neighborhoods will cover the entire x. And
right, that's what I thought. But how will you get to a constant? That's what I thought. You mean you will get I mean, of course, you will get finitely many x1, xn where you have neighborhoods around them, and that will, I mean, those neighborhood will cover the whole thing. And in each of the neighborhood, you have what? You have constant function. One,
yes.
Yeah, one. I mean, you have something like this. You have b of xi epsilon. Yeah, epsilon, say, or epsilon I, if you wish, such that its union is equal to x, and in all those neighborhood, you have one of b of this is true, one of b of x, f of epsilon. No, how will you? So you have a continuous function.
From compactness, we have only finite element.
What is that? Yeah, that's what I'm saying. I equal to 1 to n. This is equal to x. Then for each xi, you will have a f which does not vanish on this xi. So around on this neighborhood, you can say that fi does not vanish on this. So how will you get the constant? I mean, just writing it, I'm not able to write it.
So for example, you can take sigma fi.
Sigma, say it again. Sigma fi.
Fi bar.
I was to 1 to n.
Fi bar.
Yeah, so so this is a positive function. I mean, it does not take 0 anywhere.
Correct. So
inverse. Therefore, you get 1.
Inverse, and then what? I am not getting. Fi.
No, so this function never takes the value of 0.
Correct.
In the whole space, and then So therefore it's invertible, and then you get the.
Oh, you take the whole thing, which is this is a function which is okay. This is not fi bar, but then even if it is zero somewhere, it will add up and then it is not zero. Correct. This is positive and it will not cancel. That's what that's the right thing. Right. Sure. Correct. Good. So this is the point. Let me write it now. Let me see whether I can write it. Okay. So given any x naught, there exists a function is that f of x naught not equals. Given any x, for all x, there exists a f, okay, such that f of x is not equal to 0. So there exists a neighborhood b of x epsilon, okay, such that which will depend on x maybe, such that f of x is not equal to 0 on f of this maybe f of y not equal to 0 for all y in b of x epsilon. Okay. So maybe this will depend on this x. Now choose x1 up to xn such that b of x epsilon, xi epsilon union is equal to x, I equal to 1 to n. This is finitely many. Okay. Then you choose corresponding, you choose fi's also. Then the summation fi bar. This is greater than, this is strictly greater than 0 on x, right? So this implies you can, this is equal to, you call it G or something. Then G inverse G is in A, and this implies 1 is in A. Okay, very good. It's fine, I believe. Okay, good. Thank you. So because of this, this contains constant. Now it's easy. Okay, now I have taken this what was I saying? Yeah. So, but then we have assumed that constants are not there. Okay. But let me let me understand what I was doing. So we are assuming, we are defining a new algebra A prime, which is equal to A direction C, which I mean just adding the constants to that. By Stone-Weistrass theorem, A prime is equal to C of x. Okay. Now for all, so now I have to say that there exists here. So this is not possible. Okay. Suppose, what did I write? Suppose this is what I write now.
Sorry, are we assuming that A is closed under taking inverses?
Say it again.
Yeah, are we assuming that A is closed under taking inverses? Sorry, I must have forgotten the hypothesis. Or is it like closed under like multiplication from any element of the algebra or something?
No, we are not assuming anything. This is an algebra, and this is a ring, and you don't have identity there. But if it is invertible, then the inverse has to be there somewhere.
I mean, like in regular rings, that's not really true because you can have something like Z in Q, and like 2 is invertible in Q, but 1 by 2 is not. So
I don't think this is this complicated because I didn't look at anything and getting. The proofs should be easy.
I mean, I remember something similar, but instead A was like a ideal of the algebra.
Here A is not assumed to be ideal.
I know, but like I do remember like a statement that looks exactly like this, except like
this is an ideal. I mean, this when we prove this will be an ideal. A priori, we are not assuming.
Okay.
This, I mean, if you prove that A looks like this, then that's a closed ideal. It is in fact maximal ideal. Every maximal ideal will look like this. It is a maximal ideal, and indeed every maximal ideal will look like this. That's a theorem. Okay, but here we are not assuming. Our assumption is A separates points. It's an algebra. Then we want to prove A and it's closed. Then we want to prove that A looks like this. Okay, to prove that all I have to prove this A. I mean, we have assumed that A does not have constant. Then I have to prove that there exists x naught such that f of x naught equal to 0 for all f. That's what I want to prove. Then that is the x naught I want. That's what I have to prove. I mean, so this statement should not be true. What is it? Then based on this, Yeah, suppose, this is suppose. Okay. Suppose this is true. This is not true, I want to say. Suppose this is true. Suppose this is true, then I should get a contradiction. Okay. Suppose for all x, there exists a f such that f of x is not equal to 0 on that point. Then I should get a contradiction that will prove that there exists a x naught such that f of x not equal to 0 for all f in this. The assumption is a does not have constant. It's an algebra and it does not have constant. So in this proof, the inverse is a okay. So if we prove if it is inverse is there, then we are done, right? So how will we prove that? If you have
sorry, like, I mean, this is just a bit half-baked.
No, wait. Sorry. That is true here. I know it is true from, but I have to give a proof. This is true because if it is invertible, something is invertible in the bigger algebra, then it is invertible in this algebra. This is true for, this is true here. Why that is true here?
I was thinking we could do something like 1 over 1 minus f is equal to 1 plus f square and so on and so forth. And because it's a closed subalgebra, like the limiting function should also be in there.
It's not that complicated. It is, what you are saying, 1 minus?
Like, I mean, in general, like 1 over 1 minus f, we'll have like a formula which is 1 plus f square plus f cubed and so on.
Correct.
So if we can bring some function into that form, and that 1 plus f square, I mean, we have to prove that it's well defined and things converge and all that.
That is, you are
but
just.
I think that, and because it's like a closed subalgebra, the limit of this polynomial should also be there.
Correct. That is the inverse. Correct. Sure, you are right. I mean, this
So
is exactly
I think
used in, yeah, I think so. So this is like this. If you, yeah. So 1 minus f, 1 by 1 minus f will be the, so you assume that 1 minus f is, no, I think we have to prove the other way. 1 minus, you want to find the inverse of f, which has to be there. You want to approximate the inverse of f, right? So you maybe you have 1 minus f is norm less than 1. Okay. Then you can see that f1 plus f square, this thing, this is a geometric series. I mean, you can take that return, you can prove the returning by taking norm. You can prove that since the norm is less than 1, it will converge, and this will converge to 1 by 1 minus f, right? We have to prove, sorry, we have to prove 1 minus f. Sorry, we have to take 1 minus f. So let 1 minus f equal to g. Then we can say that 1 this thing will converge to, this will converge, and that limit, if you call it as s or something, then I think that will s into 1 minus g, 1 minus f. I'm getting lost. So I think this will convert this will be like something 1 by 1 minus g, right?
so I think
so
the point is
like
that f has to have norm less than 1, right?
Right. Wait a minute. Huh?
Oh, sorry. I think we should take like 1 plus f square.
1 plus f square.
I mean, because if you're
Or that
defining
you
g
should,
to be 1 minus f,
norm f should be less than 1. No? I think 1 minus sg
yeah.
1. So this implies 1 minus gs equal to, oh, that will become, it will be 0, right? So yeah, so you should have 1 minus, correct. Sure. So yeah, you should have 1 minus f, 1 plus f. So correspondingly, we have to assume there. So this will converge to S. Then this will 1 minus f times S should be identity, right? So this will, no, here it's 1 minus f to be identity. No, no, I think we have to take 1 minus G. This will converge to something like 1 by 1 minus f, right? Suppose S is 1 minus f, sorry. 1 minus f. So if 1 minus f into S should be identity, right? If I take the earlier G, 1 minus G, that will be 1 by 1 minus G. It will look like 1 by 1 minus G. I mean, you can multiply and take the limit. I mean, you will see. Let's just write it. Let me just write it. If you take 1 by 1 minus G equal to identity 1. So this implies S equal to SG. Okay. But G is equal to 1 minus F.
I'm sorry, I'm kind of confused. What is the G and the F here? So is G the same as the G defined above?
I thought so. So what you tell me, what is the right thing to take? You want to take 1 plus F, something like this.
So,
Then what
yeah,
is
so I was just thinking,
the limit is the inverse you are saying?
yeah, I'm just saying, yeah, take 1 plus F square and so on.
Okay.
And then the limit of that should be the inverse of G.
Right. So you want
So all we have to ensure is that
take
something
the
like
S,
norm of 1 minus G is less than 1.
S into F equal to 1, you want to say. S into F equal to F into S equal to
No,
1.
no, S into G.
S into, what is G?
1 minus F.
Okay. That's what. Okay. Then now it works. Okay. Yeah. Good. Okay. That's why I was confused. Yeah. Now S into G. Yes. Correct. S into 1 minus F, which is equal to S minus SF. Okay. That should be equal to 1. Yeah. S into 1 minus F is 1. So that's 1. Yeah. That's good. So you can approximate the inverse by this here. Is it clear to everyone? Is an exercise. You take this. If you take 1, so now norm f should be. It should be the case, no? I mean, if you have any function, I mean, which is bounded, of course, then you can get a function norm of infinity less than 1. Then you take this limit, which exists in norm, then that will satisfy this condition, and that will be the inverse. Okay. So because of that, if you have if the inverse exists in the bigger algebra, so this implies the following: if F is in A and F inverse exists in C01, then F is in E, because that's being approximated by this. Correct. Very good. I mean, the basic thing, this is true in a more general C-star algebra. And that is what we are proving here. Is it clear? If it's not clear to anyone, please tell me. And I'm.
Then F inverse belongs to it.
Say it again.
The last statement, F belongs to A and F inverse exists in large space C01, then F inverse belongs to A.
Correct. Yeah. F inverse belongs. Yeah, sorry, F inverse. Sorry, you are saying, oh, I wrote F. Okay, sorry. Yeah. F, yeah. Then the F inverse is actually in A. Okay, if the inverse exists in the bigger algebra, then the inverse is actually in the smaller algebra. This is a property of what are called C-star algebras, and that is true here also. Because of that, this is not true in general for algebra. So because of that, it follows. So now we have started from, I don't know whether this is this complicated. Since I'm not prepared for this talk, I haven't seen the proof. Okay, so it becomes It is becoming complicated. Anyway, thanks for the help from your side. Okay, so I think we are done. So all these things imply that there exists a x naught such that f of x naught equals 0 for all f in A. Okay. F in A. Now, so now I should have taken A. Now we have taken A equal to A direct sum C, which is equal to all those f plus lambda 1, lambda in C, in f in A. Okay. Now we want to prove that this of course separates points because A itself separates points. This contain constant. Now what do you have to prove? Now I have to prove that I have to prove that the closure of A is what do you have to prove? I have to prove that the closure of A is all those functions such that f of x naught equal to f of x naught is equal to 0. Should I take A or you should take? I'm sorry, I shouldn't have taken A. Sorry. This is another mistake. I am erasing it here. Okay, just we have read. Let me see what I have to take. We know A plus C, that is dense. So this is dense. This is equal to, this is closed and this is equal to C of x by Stone-Weistrass theorem. And we also know that this all those f such that f of x naught equal to 0, direct sum C is C of x. If you fix a x naught, you call it some A x naught or something. Okay. Then this is true. That's because any function can be written like this. If you have any f in C of x, then f is equal to f minus f of x naught plus f of x naught times 1, right? So because of that, this is in A and this is in C, of course. Okay. Now we know that so now let f be okay. So all we have to prove is following. I have to prove. So all I want to prove, I want to prove this. Okay, let me write it again. I want to prove A is equal to all those f such that f of x naught equal to 0. Okay, I have chosen a x naught such that f of x naught equal to 0 for all f. For all f in A. I want to choose that A looks like this. Okay. Okay. So now f is in C of x such that this is what I want to prove, such that f of x naught equal to 0. Then I want to find a sequence in A which uniformly approximate this f. Okay. But we know, now this is clear. We know this A, we know that A plus A direct sum C is equal to C of x. So there exists Fn in A and lambda n in C such that Fn plus lambda n converges uniformly, of course, to F. Okay. Right. Now I want to, so then now f of x naught equal to 0. Okay. So this implies Fn x naught plus lambda n goes to 0. Okay. So, but then, yeah, but of course, Fn x naught vanishes, no? So this implies lambda n goes to 0. So that's all. Lambda n goes to 0. Now f minus Fn infinity equal to f minus lambda n1 f prime. Now it's clear. F minus Fn plus lambda n This is less than or equal to mod lambda. Okay. Now this goes to 0. Maybe I have gone around. Maybe all those things are also not needed. We can use this somehow to prove this. No, we have to get a x naught. Anyway, I will check it and tell you. But anyway, now it is proved. Okay. This is let me go through what I have done. We have an algebra which separates points. Then we want to prove that this algebra, and it is closed. Then we want to prove that A looks like all those f in C of x such that there exists x naught such that A is equal to all those f in C of x such that f of x naught equal to 0. So we have first proved that it contains constant. If it does, we assume that it does not contain constant. Okay. Then we proved that there exists x naught such that f of x naught equal to 0 for all f by doing something. That's okay. Then using that, we got this. I think the proof is okay. If it is not okay, you tell me. Anyway, I will think about it again. Okay. I hope this is okay. Since you don't object, I assume that it's okay. So from this, we get the following. X is locally compact. Okay. And C0x, I hope you know this, is all those function f in, this is the functions vanishing at infinity, f in C of x, such that f is f vanishes infinity. So that is, there exists a compact k contained in x, such that mod f of x. So this is for all epsilon greater than 0, there exists k epsilon compact. This k will depend on this epsilon, k epsilon, such that f of x is less than epsilon for all x in k complement. Okay. So this is all those functions which these are called functions, continuous function vanishing at infinity. Okay. Now let x1 equal to x union some infinity, 1 point compactification. I think you studied this in topology, 1 point compactification. Okay. This is in the proof basically. Then you can see that if A contained in C0x is separates points, and f is in A implies f bar is in A. Okay. This is for complex, for real you don't need that. Okay. And closed, then A is equal to C0x. This is a Stone-Weistrass theorem, the version of the Stone-Weistrass theorem for locally compact case. Okay. And the proof is you take x1 to be this. Okay. Then all those all this f vanish at that point infinity, and it's already given. And you can see that this C0x is isomorphic to all those f in C of x1. This is compact. Okay, this x1 is compact such that f of infinity equal to 0. So you can identify with this, and from that this theorem follows immediately. Okay. So this is the version for locally compact case. This is fine. Okay. So now let me move on to Arzela-Ascoli theorem, some application of Arzela-Ascoli theorem. So that theorem says the following. Again, you consider C of x. X is metric space, compact metric space. Okay. Then you consider a k contained in this. Okay. K is compact, is equivalent to this k is equicontinuous subset. K is bounded in norm infinity, closed, and equicontinuous. Right? Okay, so this has been proved by Nirupama. So this is Arzela-Ascoli theorem, application 1. So shall I give this as an assignment? So this is another assignment, maybe 3. I will tell you the proof orally, more or less tell you the proof orally. So U be contained in C be open, okay, and Fn sequence, holomorphic sequence, sequence of holomorphic function on this, such that there exists a constant M for all compact K contained in U. Okay, there exists a M depending on K, such that mod Fn Z is less than or equal to Mk. F need not be bounded on the on the open set U, where it is holomorphic, but it is bounded uniformly bounded on the compact set for all N. Okay, there it's uniformly bounded on the compact set. Okay. Then there exists a subsequence F and K. Okay, subsequence of this Fn is just a notation for subsequence, such that F and K converges to F, which is in holomorphic function. I mean, if a function converges uniformly on compact subsets, I mean, if a sequence of holomorphic function converges uniformly on compact sets and pointwise on the U, then it is holomorphic. Okay, so all you have to prove that there is a convergence subsequence for each K. You have to get a convergence subsequence, and they are consistent. That's what you have to prove. For that, you have to use Arzela-Ascoli theorem. So to prove Arzela-Ascoli theorem, you have to prove that this, I mean, this Fn, I mean, you are proving that Fn is relatively compact. This sequence, this set Fn, the collection of this Fn, which is a sequence, is relatively compact. You have to prove. Then there will be a subsequence which will converge. I mean, which because this holomorphic U is actually a metric space. Okay, it's a function space, but it's also a metric space. So there will be a subsequence which will converge. So to prove that, to prove that it is relatively compact, you have to use Arzela-Ascoli theorem. It is bounded, which is given. No, I mean, you have to get a subsequence for each compact set and show that it is consistent. You can get a single sequence. The one thing you have to prove this, you have to prove the equicontinuity of those Fn. To prove the equicontinuity of Fn, you have to use Cauchy integration formula. So Cauchy integration formula, I mean, you have to talk about F1 of Z1 minus F1 of Z2. Okay, for all Fn. For independent of N, you have to prove. But then this is actually given by possibly 1 by 2 pi I integral over some curve of F of Z by Z minus Z1, maybe less than or equal to modulus F of I will erase this F of Z by Z minus Z2, right? Cauchy integral form. Now the whole thing just here the Z gets integrated here. Okay. And instead of Z1 and Z2, it is just I mean, it is just a constant here. You can use something and prove that there exists a uniform epsilon for all these things. What matters is this curve. Okay. And that is that depends on the Z1 and Z2. So use Cauchy integration formula to prove this. I mean, I will give another assignment, which is easier than this, which uses the same idea. So let us take a function K in C01 cross 01. Okay. And define an operator Tk from C01 to C01. Okay. By Tk acting on any F at x is equal to integral 0 to 1 k of xy f of y. This is what is called integral operator dy. Okay. You can show that this is bounded because k is bounded. Using that, you can show that it's a bounded operator. I want to, but the following thing will actually prove that it is bounded, because bounded operator takes bounded. It means bounded operator means it takes bounded sets to bounded set. But here I am going to say that, but it takes, I mean, in particular, the unit ball to bounded set. But here it will take to a compact set. TKF. Show that TKF mod f infinity less than or equal to 1 is compact. Is relatively compact. The closure is compact. Okay. So again, you want to talk about this TKF. This collection for f in the unit ball. Now if infinity less than or 1. When you take this collection, this TKF is equicontinuous, you have to prove. But then that reduces to something about one single function, because this f of y dy gets integrated here. Okay, which is bounded. This collection is bounded, which is smaller than or equal to 1. So you can take it out, and you will get something. Then k is continuous. Then you do something, some inequality, and you get this, which is very similar to what we do in the earlier one. Anyway, this assignment, this fact is used in Riemann mapping theorem. Okay, if you have already seen it, it's fine. So this is another assignment. So this is about Arzela-Ascoli theorem. One more thing about Arzela-Ascoli theorem. And prove f in C101. This is all those function such that the derivative f prime is also in C0. You take the derivative and it has continuous derivative. F in C01 such that norm f infinity plus norm f prime. That will not be there. Let A equal to, I just take this. See, the point is this. The unit, if something is bounded, I mean, in the finite dimensional case, any open ball, any bounded set, closed bounded set is compact. But if you take this in all function f in C01 such that norm f infinity is less than or equal to some m, this is not compact. This is not compact because we can take just polynomials. T power n is in here, okay? But then T power n minus T power, then you can show that this does not have a convergence subsequence, right? So this is not compact. Similarly, if you take any unit ball in general, you can prove for infinite dimensional Banach space, but Hilbert space is clear. If you take the orthonormal basis, then the difference, the distance between them is square root of 2. So infinite dimensional spaces are the bounded sets, closed and bounded sets are not compact, but something more, it will be compact. So that is what I want to prove. So you take this set, prove that this is what I want to show. This assignment is the following. Show that f is in C101 such that f infinity plus f prime infinity is less than or equal to 8. I'm just saying that f is bound. I mean, this collection, all those f is smaller than m, norm of f is smaller than m, norm of f prime is also smaller than m. Maybe another m, doesn't matter. You can just write it like this. Okay. Is compact. Okay. Again, you have to, what you have to prove? You have to prove, again, you have to basically have to prove equiquantinuity. So the bounded is all there, and it is closed is clear because of the less than or equal to sign. And no, closed is you have to prove. I mean, if some fn converges to f uniformly, and the derivative also converges to something uniformly, then the derivative is differentiable, continuous and differentiable. You have to use the mean value theorem to prove this, I think. So you prove all that. Okay. So prove that this is compact. So you have to prove that it is closed. It is bounded is clear. You have to prove it's closed. And to prove compact, you have to prove that this collection is equicontinuous. To prove that, you have to consider something like this, f of x minus f of y. But that is just integral x to y. Okay. Integral x to y f of f prime t dt, right? Then use this to, I mean, then you know that this is bounded. This derivative is bounded. The integral is between x minus y, and that is enough smaller than epsilon, something will happen. Okay. So because of that, you can prove the equivalent. So this is the assignment. I have given enough clues. Okay. So this is assignment 4 or something. Okay. 42. So that's all for Arzela-Ascoli theorem. And for Baer's theorem, so that's what I want to do. I will do in the next class. I'll stop here. If you have any problem, any doubt, we can discuss in this. Any questions?
You have to submit the assignments.
Say it again. Huh? Before midterm, you can. I mean, you better you write all the assignment each day. I mean, each week, every week, and then submit it before midterm. I will not look at it before midterm. So, but positively submit before midterm. Midterm is around March. The date is mentioned there, March 15 or something. I don't know. So before that, you submit. Okay. You can submit it by writing it, or you can LaTeX it. It's up to you. Okay. You can write it, scan it, and send to me. Or if I still, one second, let me stop recording.